Let's work an example problem, example 79.2. An oil drop whose mass is 3.3 times 10 to the minus 15 kilograms is held stationary between the plates of an oil drop apparatus. A distance of 1.0 centimeters separates the plates, and the potential difference between the plates is 340 volts. How many excess electrons are on the drop? Here's a sketch of the apparatus. I have an oil drop which is negatively charged, and it has a mass of 3.3 times 10 to the minus 15 kilograms. It's being held stationary by an electric field that's caused by this variable power supply. That's what the arrow on the battery marks is for. That battery is set at 340 volts, and the distance between the plates, parallel plates, is 1 centimeter. So essentially this is a parallel plate capacitor, if you want to think of it, that produces a uniform electric field. Now, the drop is stationary, so there are no air currents that are acting. In fact, it is as the drop falls in the absence of an electric field that Millikan was able to make a determination of what the mass of the droplet was. That's the part that you're not going to be responsible for on the AP exam that has to do with fluid mechanics, but it has to do with something called Stokes's law. Anyway, let's assume that we know what the mass of the drop is. It's being held stationary in this electric field. The Earth, through the gravitational force, pulls the drop downward, whereas the electric field is trying to push the drop upward, and those two forces are balanced. Let's sketch a free body diagram of this droplet. In many electrical problems and magnetic problems, we neglect the gravitational force. In the Millikan Oil Drop Experiment, however, the gravitational force is necessary because it's the gravitational force that actually pulls the droplet in one direction. We know the gravitational force is equal to m times g. The electrical force is given by Q times E, and we're trying to figure out what Q is. If we could figure that out, then we could figure out how many excess electrons are on the drop. We're making the assumption that we know the charge on the electron is 1.6 times 10 to the minus 19 coulombs in magnitude. So we're trying to figure out what Q is equal to. It's going to be some integer multiple of the electrostatic charge, so N essentially is what we're trying to find. Let's balance these two forces, but we need to know an expression for the electric field. For a uniform electric field created by parallel plates, we know that the electric field is equal to the difference in potential divided by the plate separation. In this case, the difference in potential is 340 volts. The plate separation is 0.01 meters because it's 1 centimeter. We can put those things together. We begin by equating the forces. The electrical force is equal to the weight of the droplet. Now let's substitute in what those different things are. Q times E is the electrical force, mg is the weight of the droplet. The electric field is equal to V divided by D. And we know that Q is going to be equal to some integer number n times the charge on each electron. Let's solve this equation for Q and then figure out how many electrons there are. And now let's put in the numbers. And now let's substitute these numbers into our calculator. I find that the charge on the drop is 9.71 times 10 to the minus 19 coulombs. If you're not sure about the units, then you can work these units out and you'll see that the charge is going to be in coulombs. A volt is the same thing as a joule per coulomb, and a joule is the same thing as a Newton meter. So I have a Newton per coulomb downstairs. A kilogram meter per second squared is the same thing as a Newton, so the Newtons are going to go. I'm going to have a meter go here, and I'm going to end up with a coulomb upstairs. Now the question is, how many excess electrons does this turn out to be? Well, if I say that there's an integer number of the electrical charge, then if I were to take the total charge and divide it by the charge on the electron, then I should be able to figure this out. Let's put in the numbers and now substitute the numbers into the calculator. I find that this particular oil drop under these circumstances has 6 excess electrons on it. Now, we did this problem assuming that we knew what the charge on the electron was. Millikan did many hundreds of experiments I don't know the exact number, perhaps you could find that on Wikipedia, observing these droplets for many years, compiling many sets of data to figure out that in fact the electrical charge was some integer multiple of a smallest charge, and that charge is what we've come to call the charge on the electron. So, now summarizing Lesson 79, we've discussed the mass spectrometer and we've discussed the Millikan Oil Drop Experiment. It's going to be necessary for you to be able to do the math on the mass spectrometer and to have at least a historical understanding and appreciation of what's going on in the Millikan Oil Drop Experiment. For now, that's it.